Okay, any questions, anything? Guess I got a few emails about the homework. So anyway, you can email me, I can kind of answer you. Yeah. Let's see. Oops, let me go back to this. Here, right? So D is oops, this guy's not there. Let's see, figure two. So do you think that the persistent length could be determined from the data given in model in 4E? So let's see, you can go back. So so he's, let's see, this is about this plot, I think. But let's see. Let me say again. D is figure 2C. It's figure 1. Oh, from this, trying to get the see, figure 2C, Do you think that persistence length could be determined from this data? All right, so the problem with this data is that so let's see. Okay. So if you should turn this on before it's gonna doing something. Flip a pen, it's good. Oh, that looks pretty good. All right. Anyway, so you have this density versus say Q, right? So if you so you're shooting radiation through something and you're going to get some pattern out of it. So the first thing you would guess is that you would get kind of a Gaussian bell-shaped curve for that, right? So that in Q is kind of like the angle, right? So you're kind of looking at this angle that it's 4 pi the lambda sine of that angle by 2. You got small angles, which are here. Sine of the angle goes to the angle. So basically, it's just a plot of the angle, x, produced by the wavelength. So anyway, so you'd expect like you shoot a beam through it, you just get a bell-shaped curve out of it. And then the main beam would be really bright, right? So the main beam's like 1,000 times brighter than this thing that you're measuring. So you have to put a beam stop in here to stop that. So then you're just detecting this kind of bell-shaped thing. So everything you shoot a beam at is going to have something like a bell shape to it. So getting Gunier, French, I realized that, okay, and then he came up with Gunier's law, which is a bell-shaped curve. So you have like RG squared, Q squared over 3. So it's squared, so it's symmetric, plus and minus Q, right? So it's got to be symmetric. It's a bell-shaped curve, so you have to square that term. And then exponential is some prefactor that's like the volume squared, the density squared. Because it's a binary interaction, that the scattering is going to arise from the interference between two things. Like if you drop 2 rocks into the water, then you get an interference pattern out. So it's a binary, so you have to square it here. All right, so see exponential, this is Gauss, that's a bell-shaped curve equation, right? So that's, anyway, so let's give you that thing. So anyway, if you go and then you say, well, I'm only going to look at this end of it, like I'm going to take the pattern that I get here and I'm going to average around. So I'm just getting the positive Q part. So the pattern, if you looked at it, would be at the beam stop and then this Gaussian thing coming out. I'm going to average around that way to get this average intensity. I'm going to look at the log of intensity versus log of Q. And then this bell-shaped curve becomes this. Bell-shaped curve looks like that when you do log. So that's the shape you're looking for if you want to get this rate gyration, which would like the normal exponential would be exponential minus like x minus x0 squared divided by 2 sigma squared. So RG squared is like 1 over 2 sigma squared, kind of for this thing with a 3 in it too. So it's anyway, RG squared is something like the breadth of this, except it's 1 over. So the broader this bell-shaped curve gets, the smaller the size you're looking at. So this is inverse relationship, inverse space. So big things are small, small things are big. So when you get a very broad thing and you have a very small thing, if you have a really sharp peak, like from a very sharp peak, you have a small q, so large size. It's like when you look at the diffraction pattern from metal, the peaks are just spikes because it's a bulk metal. If you look at the diffraction pattern from a polymer, you get these broad peaks because they're small crystals, nanocrystals, right? So if you look at nanoparticles, you're going to get broad peaks. You get bulk things. So that's basically Guinier's approach, except he's just talking about the main beam and the broadening of it. Right, RG's, if you do it through the math, then RG is the sigma squared of the thing, and you're looking for this shape, right? You're looking for a knee. And the other thing you're looking for, so that gives you a size, right? And in this business of a chain, there's 2 sizes. There's a persistence size and there's a chain size. And they're apart from each other by about 2 orders. Right? So we expect to see in this log-log plot, like with that in mind, we know this one's Gaussian and that one's rod, which means -1, -2. So expect to see like -2, then -1. Oops, sorry. And then in between, we should see like we're looking for that and that for the 2 sizes. Right. So anyway, this thing's kind of hard to see because it's actually a transition between power laws. This one should just go flat at the end. So in these plots, there's 2 sizes, the coil and the rod size. All right, so you go back to with that in mind, right? Hopefully you collected a little bit of that. Then you have to look at this plot that he has, right? So you're looking for this thing like flat and knee, and that's where you're going to get this RG. These are Guinier plots he has. So basically, let me go back there. All right, so the Guinier plot is basically, if you have that equation, let's see. So you have this exponential minus q squared RG squared over 3, and then the intensity. Then if I take a ln of the intensity, then I get v squared RG squared over 3 equals, so that's just like, it should just be linear in q squared. So if I plot log intensity versus q squared, and then I get a straight line, and the slope of that line is RG cubed over 3. If I can get the RG, this is called a Guinier plot. Okay, I mean, so this is kind of like old school, like modern, because you have computers, you just plot the log, look for a knee and fit it, right? And the old school, you take this, the problem with this is if I have some arbitrary curve and I look at a small enough segment of it, and then I plot it that way, then I can get a straight line. Then I say, I have an RG there, like I have a structure there when I don't. It's just then some kind of thing. I just picked a narrow enough region that anything on a log scale kind of looks linear. That's the bottom line, right? So it's kind of like a way, you have to be really careful when you apply this in the actual data, like the log I, log Q curve, you actually see a knee like that. If you don't see that, then there's no point in making this plot and you're kind of lying to yourself. This is a common problem, right? So anyway, so and the other thing that makes this worse is that for the persistence part, like it's going -2, -1, there is no real knee there, right? So basically, one way to get around that is to say, well, I have a -1, so I can say, I'm going to get rid of the -1 and make that go flat, and then that should bring out the knee somehow. So that's a way to do it. So you say instead of exponential minus q squared over g squared, you remove the q to the -1 part, so you divide by q out here, and then you have then you have the plot that he has. He has he says it's a rod, so he multiplies ln qi. So he multiplies, I is going to go with minus q as we multiply I by q to get rid of that rod scaling function. And that should make it better, I guess. Anyway, that's what he does, right? So anyway, so he does that and he gets this R, some size scale over a very narrow range of Q where there's like nothing to really chase after, except there is kind of a knee at when he has the pure decalan, but when he goes to the chlorinated benzene, there's no knee at all. So he's fitting this thing as if it was a knee because he picks a narrow enough range of Q that it looks like it's straight, but it isn't. So this is just flat out line. There's no size to pick there because it's just a straight line. And he does the same thing here. Yeah, there's kind of a knee there. So you could say, like, if I pick a small Q range, I can get a straight line. That's some size. But once he gets to the decalan one, there's no knee at all. Like he's just making it up. And then he just says, if I pick a small enough Q range, it looks like it's a line, so it must be a size. It's bogus, right? In other words, if he picked this region or he picked this region over here, he'd get a larger size. If he picked that region over there, he'd get a smaller size. So whatever he decided the size was, that's the size he gets out. So it's directly a straight up lie. So I mean, whether he knew that or not, you could argue he didn't know that, but basically he should have known that. And it's a stupid thing to do, right? Comparing the sizes between these is totally meaningless. In fact, there might not even be a size here, even the one that kind of looks like a knee. And then anyway, so there's a couple problems with this, but so you could say, like, can he get a size from that? Yeah, he can get one here. No, he can't get one there. And he can kind of get one here and he can't get one there. So, and the point of this is he's comparing the sizes, right? So you can't compare the size if you can't get a size. So that's what D is. That's basically what, I mean, some form of that maybe you could get, I'm not expecting you to get that perfectly, but it's kind of an example of how people, like, you have to be really careful about what people are saying, I guess. The other thing is that so he's just directly picking from the rate of gyration that he gets from that Grignard plot. And the rate of gyration isn't the length of the rod, right? In fact, the relationship is a square root of 12 between the two. So it's a pretty sizable difference. So, and then he takes that radius that he gets here and he compares it back with the radius he got from this thing, which is also messed up. So the more you look at this paper, the more it looks like it's messed up. Like things are just, he's forcing things to be certain numbers and he's forcing the fits to give the same number. Everything's forced, nothing is reality. It's just kind of a lot of money spent on equipment and samples and, like, they had to get a paper and that's it. That's kind of how it feels. Well, when you publish, okay, so you write the paper, it's got nice graphics and things, and then you send the journal your list of people that are going to review it, right? I mean, there's a plausible argument that they didn't know what they were doing. So it isn't like they cheated. So I'm not going to, like, if you do cheat, then the NSF and NIH won't give you money anymore. And your university kind of doesn't let you do research anymore. So if you cheat and then they find out about it, it's not good. But there's plausible denial here. It's like you couldn't actually prove that they were trying to pull something off, And also, so the other thing is it's a big group, right? So it's like a huge group. It involves, like, Argonne National Lab, and then everyone else is from the University of Illinois, which is like one of the top places. So no one's going to mess with them really. And they're friends with, so when you publish a journal, so you're going to send it to the editor and you have to give them 5 names, at least 5 names of people who could review it. So you put people in that are going to respect University of Illinois and Argonne National Lab, whatever. It's a network of people, right? So they aren't going to exactly rip it apart, So I don't know, there's all kinds of different mafias and cobbles of people hooked together that you couldn't prove there's any bias to it, but there actually is. So you wouldn't put your worst enemy, like they wouldn't put me to review it. So I mean, you know, that's kind of how it goes. Maybe I don't have time anyway. So, and what difference does it make? So it's just like, yeah. So you pick up a paper. So you're used to like picking up a book and it's like, and you're taught from a book, right? And then it's like, well, everything in the book must be right because it's in a book. Well, book is even worse because the book was never edited by anybody. Like this at least has 5 fake referees that looked at it. In fact, Wikipedia is probably the best because it's been reviewed by random people. Anyone that picks up it can review it and change it and fix it. So anyway, so you kind of look at different levels of what you want to trust. And in the end, you have to figure out what you believe in. And then you have to go with that and see if the evidence kind of is there to back it up, right? So, so anyway, I think you have to get used to the idea that you can't believe what anybody says. I mean, and it's a game of, it's kind of a game like a legal game where you're going with a case and there's an advocate and there's a protagonist or whatever, and they have to duke it out, get to some conclusion because something in the end has to be done. So either published or not published. It's the same thing here. It isn't a perfect system. So you have to, I'm not saying these people are bad or anything. I think they just made a couple of mistakes in how they went at this. And the more of the mistakes they made, they piled on top of each other. And then finally, they're showing that something's true in the simulation that's true in the experiment, and neither one of them is actually any kind of evidence, right? So that's the question's kind of geared towards that. But, that, and maybe if you looked at the Nature paper carefully, you would probably find similar problems, So, which would be worse. I mean, that would be much worse. So the Nature paper is much simpler. It's just like we saw chirality. That's an observation in this system that doesn't have chirality. That's a fact. So they have 2 kind of facts. So it's hard to say you could argue much against that. And that's the main point of it. This is more like analytic looking into details of it. So maybe the Nature paper is okay. Let's see. So any other things with this? I mean, I try to just kind of, if you email me, if you're really stuck, like just email me and I kind of give you the answer, whatever my answer is, which may or may not be right either. Like I'm saying, you can't trust anyone. I mean, me too. It's like you have to kind of take whatever people are saying and make your own judgment about it. So maybe you already do that, but the problem is like you're trained with these books and like they say, here's the book and this is the book for the class and this is how it works. Right. So, and to some extent, you have to accept that because you have to have a basis to stand on, but you have to always be kind of looking and saying like, that doesn't make sense to me, that doesn't actually make any sense at all. Or how did they come to this conclusion type thing, so not just in this, but in everything really, but anyway, so that's about it. Any other stuff on that or this?
No, sorry, C.
Right.
So for the 2 milligram and the
Yeah, there isn't an answer to this, right? So the point is like the intensity is proportional to the concentration. If I get twice as much in, I get twice the intensity. That's how it works. So if I divide by concentration, then the curves, if the chains don't overlap, like you don't get to the fleece, you still have just fibers, right? Then I still should see fibers, twice as many fibers, but fibers. Right. So they none of them match up with that, right? Except one. All right. So none of them work. And so the 2 and the 10 have the problem of this little rising here, which is due to specific interactions of things kind of like organizing. So you get an increase. If the thing overlaps like in the fleece, you'd see this decrease. So that's called specific interactions that lead to structure. And the other would be mean field. So it leads to like something you don't see any structure, like the fleece, So if you look at a woven fabric, you can start to see that periodicity of the fibers. That would lead to an increase in the intensity. And so this is an organizational overlap. In other words, the fibers are lining up and stacking, right? And the other one, if it dropped, that would mean they became like a mesh, like an unwoven fabric type thing, right? So you can tell kind of what's going on by the direction it goes up or down. If it goes up or down, it means that it isn't dilute anymore. Like you're beyond the overlap concentration, even at 2%, right? So, and then, I mean, what you can't exactly say that the 1% is below the overlap concentration, because you don't have a case where you have two that don't change. Like if you did a 0.5% and it was the same, then 1% is below the overlap of the coils. But since you don't have that, you don't know about the 1% either, right? And if you actually think about these rod molecules, probably the 1% isn't even low enough. You know, so anyway, and then the other thing that happens is something that you can't explain. So it could be just an experimental error, like the 20%. If you divide by 20%, if you divide by 20 milligrams per ml, you get that curve, and it isn't anywhere close. It's like an order of magnitude higher than it should be. So it means the concentration is an order of magnitude higher than what you put in. So that means that it's not a homogeneous system. It's got like areas that it has to be that if there's a mass balance, then areas have high concentrations, some have low, and your 10, 20 micron beam hit one of the high ones. That would be one conclusion just from the shift in the intensity. But if you had 20 times the concentration, the thing would be like a solid plate. So it should have a lot of this fiber thing happen, but it has none of it. So it looks like it's just individual fibers from the fleece that's 10 times more concentrated than the fleece. So it's contradictory. It doesn't make any sense. So you could say when they did when they do the measurement, something screwed up. When they did the like the sample's 10 times thicker, which isn't really possible. Or when they did the data reduction, they didn't divide by something like 10, a factor of 10 somehow, like the thickness of the sample you divide by to get this absolute intensity. So maybe they didn't divide by the thickness or something happened in the data reduction. Something's really messed up though with the 20 mg per ml sample. And none of it can really be easily explained, right? So that you're left, you can't explain that one. The two things are contradictory. It's non-uniform and it's perfectly exactly the fibers. Just the coils in dilute solution. So it can't be in dilute solution and in homogeneous and give 10 times the intensity it should have. So in other words, 10 times 20 is 200 times what the dilute one was. Like that doesn't make any sense, you know. So C's got that's a big part of C, I guess. And so anyway, any other things on this? It's kind of interesting to look at it and see how you have to kind of critically look at things. That's all. So, is that good, or kind of right. Can bury that guy then. All right. So, I guess I'm up to. I'm not sure I went through these things yet. So I just wanted to go through how far we can get in this stuff. So yeah, so the people have done these simulations to look at the persistence length, and it varies like that, like in the homework. So it's if you have high flexibility, it reaches a plateau quickly, and there's just a small kind of end effect. And as you increase the stiffness, that end effect becomes more and more of a problem. Right now, which you don't, in the top one, you don't actually have an infinite C infinity to it because you never reach it, never reaches a plateau. So that C infinity would be like the plateau value here, at least within a 50 unit chain. So this is just indexing along the chain and measuring the persistence across. And then this paper, they looked at these are all Monte Carlo simulations. This is I should say maybe what that is. So it's a different way to do simulations. You're gonna say like I have, so say, I mean, the original Monte Carlo So it's called Metropolis Monte Carlo. So Metropolis was a Greek guy. It's not a city. Like his last name was Metropolis. Monte Carlo is the city. It's like the place where they gamble. So it's a gambling simulation method. So it was originally done to kind of simulate magnets and paramagnetism, and also it's been used in composition. So you have a system that's got like X's and O's, and you can like flip from X to O. So you could take the system that way, and then randomly flip one of them to O, and then all the rest are the same, right? And then say an X and O has a certain energy of interaction. So you could sum up all the energy of interactions, XO, XX, OO, and you'd get a free energy for the system of that box, whatever. It could be 3D, 2D. Then you flip one and you get another free energy. So then you say, well, if that free energy dropped, like you always want to know equilibrium is the lowest free energy you can reach. So if that dropped, I say, great, I'm happy. You know, I'm going to accept that. If that free energy went up, then I have a problem. Like normally you would say, no, I don't like that. But I'm going to say I have like some probability related to KT, like some energy over KT, like an Arrhenius thing. It gives me a probability. And I have the temperature. And this is I can plug my energy into that, and I can get a probability. And I can compare that with a random number, the Monte Carlo thing, like I flip a coin. I get either heads or tail or whatever. So I'm going to get some number between 0 and 1 that's a probability that I get from a random number. And then at that case, I say, like, if my probability to calculate from the energy using an Arrhenius thing is either greater or less than this random probability, then I accept it. If it isn't, then so it allows me to accept things that are bad. Because you have to accept some bad things in order, because you're looking at an energy landscape. You want to reach this absolute minimum, and you're up here somewhere, and there's a lot of valleys and peaks that you have to go through. So in order to get over those valleys and peaks, you have to accept some bad things, because this actually increases the free energy, right? So this is your tests. This axis is like every time you change one of the things. So eventually you will reach this minimum thing in that process. So you can do this with anything. You can do it with like X's and O's. You can do it with magnetic moments, where the original one was magnetic moments, where you're trying to get it to go to ferromagnetic, where everything's aligned, and you start with ferromagnetic where they aren't. So you want to see the Curie transition between those two. That was the original thing. Then you could do X and O's. You can get spinel decomposition structure from that, which would be like a web-shaped structure. And you can do it for anything. So basically you could do it if you have a polymer chain and you want to see, say you move the chain some distance, and that gives you a different free energy for a system of chains. You can do the same Monte Carlo Metropolis thing to decide. So you just do that over and over again. You have small movements, check the free energy, go through your roll the dice thing if it's bad, and then just keep doing that. Then the system will evolve into a equilibrium system at some point. Like if you plot out free energy versus number of tests, it should kind of go down and reach a plateau. You reach the equilibrium of the system.
So, in that curve, you have from the energy square into 0, and then it is increasing. So it is like we are giving energy from outside, so it is increasing.
It's like if you have, say you have, I mean, you can imagine that the thing, right? So you have the chain, and then these things are hooked together, right? And in equilibrium, say they're going to be separated. I mean, this doesn't happen, but basically that could be a case. So in order for that to happen, say this guy has to go through this step where he's all bunched up here, and then finally he can go to that step. This is a much higher energy than that step, than the original. So if you said, I'm only going to take lowering the free energy, I would never unhook that thing. You'd be stuck. So the system wouldn't be able to reach its happy place, right? So there's conditions that would lead to, like, you have to get over that problem. The only way you can get over that is if sometimes you accept this thing. And then the next step, you would probably get to that thing right away. So you'd be if you plotted the free energy of that versus steps, you're down here, then you have to go up here in order to get down here. So there's a lot of things like that, where you have some kind of barrier that you have to get through. So the Monte Carlo allows you to get through that. And maybe molecular dynamics might not let you get through that. It might be that you just let them do random Newtonian motion with that thing, get through that to that. Well, if a high enough temperature, maybe you would. No, it's just a different way to do it. It doesn't involve, anyway, so mostly people write their own Monte Carlo programs. Like it isn't something that people usually do out of a package like lamps. Like molecular dynamics is easy. So pre-packaged, so you just take it and implement it, and it's already been done. Everyone has their own Monte Carlo. So they're doing that kind of thing for this bottle brush polymers. So it's like it's a polymer with a lot of side groups on it. It looks like a bottle brush. Anyway, so that became a common thing in polymers to have a bottle brush. And they can see the persistence for linear chain. And this is comparing different chains that have different molecular weight. So if there's a lower persistence for the short chains and a higher persistence when you reach a C infinity and it plateaus out. That's the idea. And if you put a lot of high density of branches, you get a higher persistence. It takes it longer to plateau. Low density of branches is kind of a trend here in that thing, right? So anyway, so they try to model it with a power law. Like you can do a power law that it kind of looks okay. Then they try to model it with this kind of ad hoc equation that's looks like a Maxwell equation for relaxation, where you can have this kind of shape of a curve from a Maxwell relaxation thing. Like say this is a piece of goo with a weight on it and it's stretching down, so the strain increases with time. Then you'd have an equation like that to talk about the goo dripping equation. It's got a dash pot and a spring hooked to it, right? So anyway, so in this case, they put in the branch length and they can get a pretty good fit to that. This is a log. So these are kind of, so what are these? The parameters are like meaningless in both of these. It's just like there's 2 parameters in the power law. This thing has 5 parameters. So basically you start to wonder like what's going on with these things. Anyway, so you might think this, the Flory-Fox equation, which is for glass transition, deals with n groups. Right? So you have Flory-Fox, you had glass transition versus molecular weight, and the glass transition increased with the molecular weight somehow, right? It reaches a plateau at some molecular weight. So I guess it kind of looks like that. Right? It looks similar to these curves actually. So you have TG is TG of an infinite polymer chain, and then minus 2 some constant like Flory-Fox, this is FF over the molecular weight. Because for every chain, there's 2 ends, right? And the fraction, so if you said like the chain has a fraction ends, it would be like the total molecular weight, and then so 2 over the total like n number of units would give you the fraction. That's like a fraction of n's. So this thing's like the fraction of n's, and then as the molecular weight goes higher, it gets a smaller fraction. So that thing drops, and you end up getting this thing. Right? So you could say, well, you could use that Flory-Fox approach, the n group approach, because it's an n group effect, because it's at the ends, to talk about this persistence length. You could say, well, it's going to follow that equation like the Flory-Fox equation. So this kind of flexibility thing diminishes as the molecular weight goes up, and that kind of roughly gives you something that looks like that behavior, right? So anyway, that can work sometimes. This is 1 over the molecular weight versus the n group versus the persistence, and you kind of get something kind of linear with it. But all right, so there's another way to kind of look at this thing. So we have, let's see. So another way to look at this is that we had these tangents, like S and 0 tangents. So persistence length is defined by this exponential minus S over LP, right? Which looks a lot like the absorption coefficient. Like we have the I over I0 equals exponential minus absorption coefficient times length, right? So it's like, here you're not looking at, this is 1 over LP equals some kind of like absorption coefficient. So here, if you want it, if you have a composite, you're gonna have like volume fraction, one component, and then 1 minus that times the absorption coefficient. So the intrinsic parameter is the absorption coefficient, not the absorption length, which would be 1 over alpha. Right, so anyway, so it looks like 1 over in this kind of exponential decay is the parameter that you want. Alpha for a composite is like the fraction of each. So basically, the LP isn't exactly the parameter of interest. The kind of the flexibility coefficient or something is like the thing of interest, like this 1 over LP. If you want to make an analogy with linear absorption, right? So you can do that, and you can take that same data and you can get something that looks kind of linear. If you do that, so you can get these things to match up, and then you can also, but this is this Yithra data where he's doing a higher molecular weight than the Connolly thing. This is the Connolly, that's Yithra. This is this Connolly group. So Connolly's got lower molecular weight than Yithra. Yithra's got higher molecular weight. They both use Monte Carlo to get this, and they're both looking at brush polymers, right? So this thing works with Yithra's high molecular weight stuff. It's linear. When you do that with Connolly's thing, 1 over LP, and then you get this problem that it plateaus out. And these are really low molecular weights. This is a 10.1 means he has 10 units in the chain, right? So you need to kind of add in another term to that to get that to work, like the persistence of the 0 unit, and then you can get this to fall. Like you can get a perfect match with that equation. The nice thing about this equation is all the parameters mean something. Like you have your infinite molecular weight, length, infinite molecular weight persistence, the 0 molecular weight persistence, and then molecular weight, and this thing is like the rate of change due to the n groups. In other words, how much K is kind of how impactful in other words, what's the structure of the chain that's in the K, right? Kind of the local flexibility of the chains in K. I mean, local flexibility is in LP0, the impact of that on the chain persistence in K. Right, so you have 3 parameter fit instead of 5 that can fit everything. So it's kind of maybe the answer to that business. Anyway, so that's that, yeah.
Specific polymer systems that's the 5 parameter model goes to accurately predict the specimen.
It kind of predicts, right? But basically, it kind of predicts it for the low molecular weight from Connolly. This is Connolly's equation. The problem is like the A doesn't mean anything, and the B doesn't mean anything, and the N doesn't mean anything. Like none of the parameters really have any meaning. It's like if you wanted to calculate them, you can't calculate those things. But the infinite persistence length has a meaning. It's like it's like how the chain structure itself contributes to the rigidity of it. How tethering the units makes them more persistent. And the 0 is like the thing maybe that they calculated in this paper this week. And when they do that molecular modeling of the small unit, that's a 0. And the K has something to do with how the thing's put together. So I think the other way you can say like what the terms are instead of A, B, and whatever. All right, so that's the advantage, I guess. But all right, so is that business. Then I talked about this already, this Flory stuff. I may have briefly talked about it. I think that's good enough. Like we don't need to dwell on that. And I went through the persistence. That's this week's homework. And then we've gone significantly through neutron scattering. So, all right, so then we have this thing of the polyelectrolytes, like medical kind of polymers or biological or surfactants and soaps and things like soft matter things. So we're talking about having a chain that's got charges on it. You know, so somehow in simple cases, you have some chain, and then suddenly you put charges on it, and it straightens out basically. Right. So this chain has a persistence length. And then this chain has another persistence length that's going to supposedly, I mean, the way this is done is L0 plus L electrostatic. You're just going to, I mean, this is how it's looked at, is an additive term. Generally, like this, that term is much larger, like much larger than the L0. So this L electric is bigger than L0. So this is a dominant feature of these chains. So this is like proteins, nucleic acids, like surfactants, and coacervates. Coacervates is if you have like a polycation and a polyanion, and you mix the two together, they'll form kind of coupled pairs. And that's basically like goo. That's like all of your phlegm and things in your body. That's what phlegm is. You know, it's basically the positive and negative proteins are just binding up and making a gel. Right. And that's used in a lot of consumer products too. So it's kind of like an additive for like Procter & Gamble and Jergens stuff. You know, so people are interested in this kind of coacervation thing. What else? Anytime you put a polymer into water, it's usually a polyelectrolyte. So hand gel, basically gooey stuff, you know. So it's of importance to people. Anyway, so the idea is that if you have, say you have a charge, this could be a chain, or initially this is just like a surface. It's got a charge on the surface. Like it could be silicon, and then you have hydroxyl groups on the surface, silicon or silica, and there's silanol or siloxane, silanol or hydroxyl groups, OH groups on the surface, negatively charged. And then you have a solution, and usually the solution is going to have like ions in it, like salt, you know, so it'll be like sodium chloride floating around in the solution. So the negative surface of the silicon or silica will attract the positive sodium ions, and they'll form a layer, right? So you can form a layer there. Then you can also think about, then there's the bulk concentration of the salt out here. So you can say, you could plot the charge as a function of distance from the surface, right? So that's this this Goy-Chapman potential equation. Right? So you can have something like an exponential decay of the charge going from the surface. If the fluid is flowing, which it usually has some kind of motion, then there's a point where the charges, where the flow energy overcomes the charge binding energy, and then so there's a shear plane. Like, so the charges are going to have like a complicated profile, but generally it's just an exponential decay going down. And then so this kind of, and then at different points of that decay, you could define these different, there's a surface potential, there's a potential for the monolayer, the Stern potential, and there's a zeta potential that has to do with this diffusive layer. So you have these charges going away from the surface that you're talking about in this business. Anyway, so the bottom line is that this thing's described by this exponential decay generally. I mean, there's these nuances to it, but basically there's an exponential decay. And 1923, Debye kind of came up with this Debye screening length idea. So this is called kappa. Sometimes it's called lambda d. Sometimes it's one minus, the inverse of kappa is called lambda d, or something else. Kappa, 1 over kappa, lambda d, and one other thing. We'll see it in these notes, I think. But so basically, this number is talking about that there's other ions here, so you lose the ability to see the charge on the surface at some distance. So the device screening length is the distance you get away from a charged particle that you can't sense the charge anymore. Like this decays down to some point. That point is where the motion or the energy between the counterions and the surface becomes smaller than the KT energy that's making everything shake around. So when the KT matches the potential of the particle of the counterions to go to the surface, that's the device screening length. And beyond that length, the charge is washed out. You can't see it at all. There's no effect of it. So you have to be within a certain distance to feel the charge. That's the idea. So there'll be no effect if you get beyond the screening length. All right, so how do you increase screening length? So say you wanted to get rid of the charge effect. So if you did that, there's a dramatic thing is going to happen. Like you're starting out with say you have this rigid chain with these charges on it, and then you're adding like sodium chloride to it, right? And then all of a sudden it's going to go to this squiggly, like it's going to be a huge transition. The persistence is going to go from like 100 angstrom down to like 10 angstrom. And the coils, the size of the thing's going to go from this huge thing that's charged to that little teeny thing. And the huge thing is charged, if the concentration is high enough, is going to organize into structures. And this thing is just going to be a messy goo, right? So by adding salt to it, you can get this weird thing. So that's called salting out for soap. So soap is like this, it's got charge things in it. So you can do there's a video of this. Of soap. So this is the process that they originally used to make soap, like when Procter and Gamble were in Cincinnati. And then this is the thing I looked at this morning, but I don't want to play this. Actually, I want to see number 2 of it. So she takes the soap, puts it into water, gets it to dissolve. And then she gets this weird, disgusting, like soup thing of soap. And then in part 2, which is the part we want, I don't know how to get to 2 except go through this.
It's probably unavoidable.
Let's see. I want to see part 2.
I believe the first one.
Where is it?
First one, top left.
Top left.
On that. Yeah.
Oh, this. Okay, thanks. All right.
Back in store.
I don't want to hear. Oh,
Yeah, that's-
listen to this or something. Okay. Right. So anyway, she throws the soap in,
And-
dissolves it.
Now,
Oh wait, is this the same person? Is it?
I believe.
It's the same thing though. So anyway, she dumps the salt in, and then it goes from that mess, and then it goes through applesauce. She tells it, and then so things are happening, and then finally on the top, you just get a solid soap, and on the bottom is water. So what happens is all the soap are these fatty acid chains, and they crystallize into like a wax. And that's your bar of soap that you have. And then all the salt is still in the water at the bottom. So you've screened all the charges on it so that they can approach each other and crystallize like a wax, so as if they're uncharged. Right. So that's the process they use to make soap. Because when you make soap, you start with a fatty acid, a triglyceride. So you have glycerol at the top, 3 OHs, and the OHs are attached to like wax chains. Right. This is glycerol. So you break that apart by putting it into lime, like a base. That'll rip this off, and you just get the glycerol, which is like fake tears, or all your cosmetics have glycerol in them. Then these things are these chains with an OH on the end. Right? So basically these are what soap is, like an Na plus and an OH on that chain end gives you this, right? See, it's a carboxylic acid with 12 carbons down, right? So basically that's the soap. When you put in salt, it screens that charge effect that makes it want to make like micelles around the fat. Like the fat sticks here and the charges go to the surface. You make a micelle. when you put salt in, it breaks those apart, and you just get, these will just crystallize into soap, into like wax, you know? So anyway, so that's salting out. As you're adding the salt, what you're doing is decreasing the Debye screening length. Let's see, so. All right, so that if you watch that whole video, it's really gross, like, if you're like cooking soap, it's really gross, but anyway. So this Debye screen length goes with the N is how much the concentration of salt that you put in, right? And then that makes the thing, this RD gets so small that your distance between the things disappears. In other words, the distance between the charges gets so small that there's no charge effect in the system. So you can salt out polymers, polyelectrolytes too, the same way, right? Is that a question or is your arm broken?
Yeah.
Okay,
So,
or both.
Yeah.
Yeah.
So it seems like the salt pulls the OH out of the chains to like get it the fatty acids ready to turn to salt. It's not salt.
Yeah, all right, I didn't explain what's going on. All right, that's good. So you have a bus station, right? And no one's in it. It's a huge bus station. And there's a mother and there's a little kid that's screaming, right? So
Okay.
the Debye screening length is infinity. Like the kid could be anywhere in the world and the mother would see it. Like there's some homing instinct. So say plus minus. Then it starts to get crowded, right? So there's some other like minuses showing up and pluses. So things get more and more concentrated. So there's some distance and everyone's screaming, like they all have babies. So basically there's some distance that she can't identify her baby anymore. She can't hear it at all. Like she doesn't know the baby's crying at all because it's just a cacophony of screaming. So that distance that she can get away, that's the device screening length for baby screaming. Right. All right. So there's another distance involved here too, which was discovered in 1926. This 1923 was the Debye, and then 26 was the Jabirum length, the BEJRUUM or something. Right. I think it's like Norse or something like that. Some weird name. Anyway, so that's a distance. So she can, at some point, she can't tell where the baby is, right? But she can still tell it's screaming. Like she can identify her own baby's voice. She knows it's screaming. She knows she's in trouble, but she can't tell where it is, right? So that's different than not knowing the baby's crying. There's two questions. Is it crying or not? The other is, where is it crying from? And right, so the Debye screening length is out here. The Beaucage length is like inside a little bit, this LB. And that's going to decide which way she's going to run. Like she's going to run to the baby, so it's directional, right? In other words, if you're within the Beaucage length, you can form a crystal, right? If you're within the Debye length, something's going to change. Like you're going to ask people, where is my baby? So something changes. But if you're beyond the Debye length, it's as if the baby doesn't exist, right? So there's these like three different regimes, yeah.
I'll ask a question before we wrap it up, but it's based on the end group functionality. I want to know if it influences the persistent length of both branch and linear polymer.
Yeah, that's what those plots were. What did you say? It affects the persistence length? Yeah. So that's the idea. Like you add in this, you're saying, does the side groups change the persistence length? Yeah, so yeah, I mean, that's what the point of those papers are. And kind of, you can have the steric interference to make the persistence go longer. Yeah. Yeah, there's a direct impact. It's, yeah. 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 Then she senses it, so something is going on. So that in that condition, it's a mean field. So she can't tell where, so she's not going to make a crystal, but she changes her behavior, right? So that's called a mean field. You have a field that's affecting you, the screaming baby, but you have no idea where it is. So it's an average field. The direction is within the Beaucage length. That's a specific interaction. You're going to specifically go to your baby. But the other is like, the baby's crying and all you can do is scream, where is my baby? right? I mean, another thing would be like you have a guy with a gun and he shoots the gun, you know? So if you're too far away and there's other people shooting guns, right? So it's in a war. So basically, if you can tell where he is, you can run away from him, right? So that'll be within the Bajiram length. If you can just hear his gun and you're going to just cower, that's within the Debye length. And if you do nothing because there's too many guns going off all over, it doesn't make any difference. Then that's outside the Debye length. You know, so there's no effect of it at all. It's like you've gotten used to guns going off. So it's like that's it, right? So yeah, anything like that. So it's a general. I mean, it's important to get the idea that this is a general idea in nature. Like it isn't just charged particles. Like any kind of interaction, any kind. So we'll talk about like the Flory, like we saw the screening of structure. Like so, it's the same kind of idea. There's a point where you reach concentration where you can't see, so the thing doesn't exist anymore. That's the key element of how Flory figured out that a polymer in a melt would be a random walk. It would cross itself because once you get to such a concentration of polymers, then you can't see the other polymers and it just acts as if it's random, like an ideal chain, even though it's so concentrated. There's a screening of the enthalpic interactions. So this screening idea that Debye came up with that had ramifications beyond, it was really important to biology, but it had ramifications beyond, and soap making, but beyond that into other fields, you know, because suddenly this concept of a length scale that has to do with where you don't see the interaction anymore becomes important for things. But all right, looks like I've successfully wasted an hour here. Any other stuff or wait, I guess. That's a pretty good question. I don't know. I don't really know. I have to think about it a little bit. In other words, there would be no mean field regime. The mean field regime would disappear. They're kind of different. So the Bajiram length doesn't have a counter ion concentration on it. So yeah, I mean, I guess if you varied the counter ion concentration, you could tune the Debye length to equal the Bajiram length. The Bajiram just involves KT and the charge. The balance of the initial charge of KT. The Debye length also includes the screening thing. So there's no screening in the Bajiram, it's just KT and the charge. So yeah, you could get them by changing the counter ion concentration. You could get the Debye to come over the Bajiram, I guess. I never heard of it. The idea mostly is that the one's smaller than the other. So you have this gap where you have a mean field behavior, which is important to polymers because that mean field is the basis of almost all the calculations people do. Because once you get to specific interactions, you can't do calculations anymore. It's too complicated because you have to do binary, ternary, quaternary, and it has to organize and will make a crystal or something. Like that's a big problem, like trying to solve that. Right, but the mean field, if you could just say there's no direction to it, it's just a linear equations, you know, so everything's really simple. So everyone wants to get to mean field. They're trying to avoid specific.
It started.